briefly, but we spoke about this notion of the abstract data type, the ADT, which is like a specification. It's like a specification of operations on data. So the list, as it's called, supports insert, find, and delete. There are related to lists are the ADTs of stacks. I'll just say stack and queue. So unlike a list, which supports insert, delete, find, it supports more. You can do more things, fancy things with lists. Stacks and queues are relatively simple data structures. So they only support two operations, which essentially it's like they support an insert and a delete. There's no find, except in a stack it's called a push and a pop, and an insert it's called an NQ and a DQ. So these are the names of these operations. So you never say you insert into a stack. Typically you'll say push into a stack, and you pop from a stack, and you NQ and DQ into a queue. So how many of you have seen stacks and queues before? Okay, good. So most of you have seen it, so this should be reasonably familiar. So in a stack, it's called LIFO, which is last in, first out. So what this means is you delete or pop the newest element inserted, and this is called first in, first out. It's FIFO, which is you delete or you DQ the last element inserted. So stated as this way, I've only specified the operations that a stack supports. So the stack abstract data type basically supports what's called a push, which is insert at what's called the top of the stack, and a pop, which is delete the top of the stack. Sometimes you'll see when there's a discussion of the operations of a stacks, there's also something called a peek, which is get the top of the stack, but don't remove it. Right? Again, you can implement a peek just by doing a pop and a push. Right? So, but just so that if you ever see this terminology, you know what it means. Peek is to get the top of the head. It's the top of the stack. Okay. Any questions about that? So, and if you think about the implementation of a stack, our linked list is already an implementation. Because if you look at the inserts, we always insert at the head. So to push onto a stack is to insert at the head, and to delete or to pop is to just delete the head. Right? So you just remove the head. So we already have an implementation of a stack through our linked list. So I just want to make this distinction clear. Right? You use the linked list to implement a stack, and then you have a stack data structure. You can use a linked list to implement a queue, but often you need a tail pointer. You need a pointer at the end, because when you insert, you want to insert, or you want to delete at the end, not insert, but whatever. Right? You don't want to delete and insert at the same place in the queue. So I'm going to talk about stacks for maybe the next 2 lectures. So I'll just say that a stack can be implemented as a linked list. So I will provide you with my implementation of a stack using a linked list, which you can play around with. So does this work? So here is your linked list. And if you want to push an element onto the stack, that's the same thing as just inserting, right? Because if you insert, then the head will point there. And to pop is to just delete the head. Right? So deleting the head is really simple, right? All you do is you just say that you could just say head is equal to head arrow next, and then make sure that this is null. Right? Store this in a temp. Store the head in a temp. Make head is equal to head arrow next. Temp arrow next is null, and then return the temp. That way you return the first element of the stack, the first element of the linked list, which is popping the stack. And if you want to do a peek, this you can just return the head, return the value at the head. You could return head arrow. So I'm not going to talk as much about implementing a stack because I think it's fairly clear. What I want to talk about are actually the interesting uses of a stack. Okay, questions? Right, all good? So what is the classic use case of a stack? Does anyone know? Well, I mean, there are many answers, but what do you need a stack for? What do you do with a stack? Yeah? You what? Oh, that, yeah. Yes, okay, that is a classic example. Not the one I'm going to talk about, but yes, you can do that. What do you do with a stack, yeah? Is used in recursion, yeah? It's the call stack. It's the call stack. And that we will talk about quite a bit, yeah? Yes, you can check if parentheses, right, are correct. So that's like a classic example of a stack. So it's used in parsing. When you want to parse text, like if you, in your browser, it gets HTML code, right? How many of you have seen HTML code? Some of you. Okay. Some of you have seen HTML code. You see there are tags in HTML code. And it has to match like the head open tag to the head close tag, the bold open tag to the bold close tag, so on and so forth, which is this problem of checking parentheses. So quite simply, here is a correct parenthetical statement, and here is something that is wrong. So this is correct, and this is wrong. Right? You see that this is not matching up parenthetically, whereas this is a correct parenthetical statement. Right? And so a question is, given a string of parentheses, is it correct or wrong? Does that make sense? I give you as input a string of parentheses, is it correct or wrong? And you can solve this problem using a stack. So I'll talk about how you use a stack to solve it. Once you see it, it's pretty, it's not very complicated. It's a clever algorithm though. So, and where does one actually use this? Well, if you look at HTML code, you'll often see tags of this form. And you see lots of different kinds of tags, right? So on and so forth. And so what this means is whatever is in this portion is like, the head, and whatever is in here is a paragraph, and so on and so forth. And you have lots of different tags. And so when HTML is actually processed by your browser, it has to parse the text, meaning it has to break up the portions in the head, paragraphs, and all that. And usually if tags are mismatched, then it will try to do its best. Yeah? For calculators, yeah. So you can use a stack also to build a calculator. Like if you get an expression you get like an algebraic expression, a mathematical expression in this with basic operands like plus, minus, divides, and multiplies, and parentheses, then you can use a stack to do that, which is also what's called parsing. Right? So all of these fall under parsing. So if you do a compiler's course, you'll see stacks appear again in how to actually take a piece of code, or even like code that we write, like this code here, this code that we wrote over here. Right? Your compiler has to parse this code, and so it has to deal with parentheses because it says, well, here's the big parentheses, here's one inside, here's something else inside, here's something else inside, so on and so forth. So it actually uses a stack to figure out if your code is correct, or at least not correct, but is parenthetically correct. Does that make sense? So this is which you'll see in compilers, and that's why stacks appear a lot in that. So let's first, before, how many of you have seen the stack algorithm for parentheses? If everyone has seen it, then maybe I will move on. No. Very few. Okay, all right, then let's talk about it. Okay, so let's start with a simple case. Suppose all parentheses are of the same type, meaning that you only have this or this, right? So I'm going to give you a string of symbols with open and closed, right? So I give you whatever. And I say, is this correct or not? No? Okay, I don't know. I just wrote something at random, so it's likely that it's wrong. But so I'm going to give you a few minutes to think about it. Again, you can talk if that helps. Come up with an algorithm. It's a very simple algorithm. You don't even need stacks. You don't need stacks. You don't need linked lists. You don't need anything fancy. Single for loop. How do you determine if this is correct or not? Okay, so I'll give you a few minutes to think about it. No stacks, nothing. It's much simpler than that. Okay, so how many of you have or think you have an algorithm? Okay, some of you. Okay, then let's think about this. So I'm going to give you a hint, and then I want you to think about it again. Is you only need one counter. Okay, a for loop with a single count variable. And what you need to do is you need to do something every time. So as you process this for loop, as you process this in order, every time you see an open parentheses, do something with the counter. Every time you see a closed parentheses, do something else with the counter. Look at the value of the counter, and then determine if this is correct or not. So now let me think about it. Okay. Do now more people see how to do it? Yeah? So the trick is, when there's an open parentheses, increment the counter. When there's a closed parentheses, decrement the counter. So start the counter at 0. So initially it's 0. So it's going to become 1, 2, then back to 1, 0. Then it's going to go 1, 0, 1, 0, then 1, 2, 3, 4, 3, 4, 3. I hope you understand. Like, it sounds like I'm just randomly giving out numbers. Hopefully this makes sense. I've forgotten where the counter is. So, but anyway, eventually you'll see that I think at some point, if the counter becomes negative, then you've seen more closed than open. So obviously, it's not correct. So if you ever see a negative number, then it's incorrect. And when you finally end, you should end up with 0, right? Because the number of open should be the number of closed. Mathematically proving this is correct is a little harder. It requires actually something called induction. But you have your hand up. Good. So if it starts with a closed parentheses, your counter starts at 0. If it starts at a closed parentheses, the counter becomes -1, and then it fails. So I'll just let me write down a few lines, and then just a second. And if you're asking what this has to do with stacks, I mean, trust me, there is something. So let me just make sure that okay. So I'm just going to set a count equal to 0. And then I'm just going to run, I'm just going to write the pseudocode sort of in English, right? For each character in order, right? So you're going in order. So this is just a loop. So my first is, if the character is open, then do count plus plus. So increment the counter. If the character is closed, count minus minus. And if the count is less than 0, output wrong. And so finally, when this ends, we'll say if the count is strictly greater than 0, output wrong, else output right. Okay. Does that answer your question? Yeah. Right. Okay. Yeah.
If we're doing it this way and we have 3 different kinds of brackets.
Good. Yeah. I mean, you're getting ahead. So that's what I was going to ask. All right. So is that clear? Okay. So now forget 3. Suppose there are 2. So I have this and this. Right, so I have 2 kinds of open symbols, 2 kinds of closed symbols. First question is, can you give me an example where so I could basically change this by just saying if the character is open, increment the count. If the character is closed, decrement the count. But you can see that's wrong or that algorithm is incorrect, because if I have a parenthetical statement of this form, this algorithm here says it's right. There is 1 open and 1 closed. So obviously it has to distinguish between the types. So now what? Yeah? Okay, so you could have 2 different counters. One for the parentheses and the other for the square brackets. That's wrong. Why? Someone give me, okay, I'll pause. Think about it. So question makes sense? So you could have 2 counters, right? Instead of having 1 counter, you could have a counter for the parentheses and the other for the bracket, the square bracket. Right? So you have 2 counters. Now I'm saying that even that algorithm is going to make a mistake. And there's a simple example with 4 characters where you can see that. So I'll give you a few minutes, but figure it out. There's an example with 4 characters where this algorithm will say it's correct, but actually it's not a correct parenthetical statement. Okay, I'll give you a minute. Okay. All right. So do you see who has an example where it's going to fail? All right. Yeah, in the back. Yeah. Exactly. Right. That's the example. So if you have two counters, like the first counter for the parentheses is going to work, and the counter for the square bracket is going to work, but they're sort of interleaved the wrong way. The problem with the counters is they're looking at each type separately. They're not able to combine the information. And so the solution is a stack. So what a stack effectively does is it interleaves the counters the right way. That's basically what it does. So I'll write out the stack-based algorithm. Again, I'm not going to write it as code specifically. I'm just going to write it in English so that you get the idea. So you start with an empty stack that I'll call S. Then I'll say for each character in order, if it's an open, I'll say an open character, but hopefully you know what I mean, right? If it's an open kind, then push onto S, or push the character onto S. If it's closed character, suppose it's a closed character, then what do you do? Okay, yeah, you pop, yeah? Right, so you basically pop the stack and check if it matches the closed character. And if it doesn't match, you output wrong. So what you'll observe is the stack only has open characters, which is like your counter. Your counter is only increasing when it has an open character. Okay, so I'll just write this down. So if it's closed, pop S. If the popped character matches the closed character, well, okay, I should say doesn't match output wrong, right? And then finally, if the stack is not empty, output wrong, else output, correct. So if you think about the character-based, the counter-based algorithm for just one type, the counter is just the length of the stack or the height of the stack. The counter is just tracking how many elements are on the stack. And this, of course, because it has different types, is kind of interleaving those things. Yeah, question? You're not popping. You're right. You're right. So I guess I should say that if, well, okay. So if S is empty, output wrong. Thank you. Sorry, it's a bit messy. But if it's a closed character, if the stack was empty, you output wrong. Otherwise, you pop and you make sure it matches. So the best way of understanding this is to really take a small example and run it yourself. Okay. Again, it's not, if you've never seen this for the first time, it can take a while to understand. If you've learned nothing else from today except that you can use stacks to check parenthetical statements, then you've learned something useful. People do ask that question. So we're at about an hour through our time, so let's take a break for a few minutes. And when we come back, we'll start